Yeah, and the goal is to know when they converge. Okay, so here x is unknown. Think of it as unknown. And you want to find values of x so that it converges. All right. Yeah, and we have three scenarios for a power series. A power series can converge for all x. That's case one. We say the interval of convergence is all reals. The radius is also all reals, meaning that no matter what you plug in for x, it's going to converge. We have some power series that converge almost nowhere, okay? The radius of convergence is 0. There is no interval of convergence, but the power series does converge when x is equal to c, because when you put c here, basically every term becomes 0, except for the constant. And then we have power series that converge on a finite interval and diverge everywhere else. Okay, so we have an interval of convergence. There is a finite radius of convergence, and we don't know what happens at the endpoints. Okay. Jose is asking, do divergent series have any applications? I don't know. The series are, again, Jose, one reason that people begin investigating series is because of integrals, improper integrals. If a series converges, then the improper integral converges, vice versa. If the series diverges, then the integrals divergent. I mean, that's mainly the application. If you can't evaluate an improper integral, you do the series form of it. But no, I don't think so. Application. Maybe they do, maybe they don't. In order to know when I say when means that we want to find x. In order to find x so that the series is convergent, we are going to find the limit. So again, I'm reviewing. We're going to find the limit of the ratio in absolute value, and we'll make it less than 1. Okay, I will write this down. So to check or to find the interval and radius of convergence, we find all x so that the limit as n goes to infinity of absolute value of u sub n plus 1 to u sub n is less than 1. Okay. Yeah. This is an inequality. And this inequality by ratio test tells you that the series is convergent, or more specifically, absolutely convergent. Okay, so if this inequality is true, then the power series converges absolutely. Which means it's convergent. If a series is convergent, then if a series is absolutely convergent, then we know it's for sure convergent. Okay, remember, absolute convergence means convergence. Okay, and I did an example. So let's do more. Let's say we have this series and going from 0 to infinity of n factorial times x plus 5 to the power of, let's say, n. Okay, so notice that in this power series, if you want to identify the coefficients are given by n factorial. So remember, this is the form of a power series. A sub n are coefficients, then C is the center. So here the coefficients are given by n factorial and the center is, can anyone tell what the center is?
What do you mean, -5?
It's -5, yes. It's x minus -5. So the center is -5, okay? If you write this in the form x minus c to the power of whatever n. But I mean, we don't need to identify those, but we want to find x so that this power series is convergent. Okay, so before we do any work, let's speculate a little bit. Notice that the coefficient is n factorial. And this is an exponential thing. This is an exponential factor. This is a factorial. Remember the order of functions, the order of sequences. And factorial is more powerful than exponentials. Okay, so the order is r to the n less than n factorial. And that is less than n to the n, the most powerful. And factorial grows much faster than exponential. So no matter what you plug in here, this n factorial is just gonna overcome, okay? Meaning that as this gets small, so you can choose a value for x so that when n grows, this gets small. Like imagine you choose negative, or let's say, negative 4.9. Imagine you choose 4.9 for x. Okay, so here we get n factorial, and here we get 0.1 to the power of n, and the summation of that. As n grows, this goes to 0, right? 0.1, the basis between 0 and 1, so the whole thing goes to 0, the whole thing. But this goes to infinity. But since n factorial is growing much faster, then infinity is going to take over. So terms of this series are not going to get small. Terms are just going to blow up as n grows. And you're adding a bunch of numbers that get big and bigger. So this power series is just going to diverge no matter what, except for when x is -5, it will zero out, everything will zero out except the constant. But for anything other than -5, this is going to diverge, okay? Well, you don't need to speculate like that. You don't need to. It's just something that you could see in advance or predict in advance, but we are just gonna do the math, okay? So again, we want to check absolute convergence. Here our u sub n is n factorial x plus 5 to the power of n. And what you do is you find the limit of the ratio in absolute value right, so we get n plus 1 factorial times x plus 5 to the n plus 1. That's our u sub n, and then u sub n plus 1, and then divide by u sub n, which is n factorial x plus 5 to the n. All right, so let's simplify that ratio. Expand a sub n or u sub n plus 1, n plus 1 factorial expands to n plus 1 times n factorial. X plus 5 to the n plus 1 is x plus 5 to the n times x plus 5, and then leave u sub n untouched because it's just going to get canceled. Okay, now do the cancellation, and factorials cancel, x plus 5 to the n cancels. We end up with the limit as n goes to infinity. Now, things that can come out of absolute value should come out of absolute value. For instance, n plus 1, anything has to do with n comes out of absolute value because n is going to infinity. Remember, n is a natural number. Okay, it's 0, 1, 2, or it's just 1, 2, 3, 4. N can't be negative, n plus 1, therefore can't be negative. Absolute value of n plus 1 is just n plus 1. But since x is the variable, x could be anything. X could be, say, negative 10, it could be negative 100. It could be 10, 100, a million, negative million. Then the sign of x plus 5 could be positive or negative. We don't know the sign of x plus 5. Therefore, you must keep that in absolute value. Okay? Yeah. And again, the condition for convergence is that this has to be less than 1. So after you simplify and everything, okay, don't take the limit yet. After you simplify that ratio, set it less than 1 because we want it to absolutely converge. All right. And now you have yourself an inequality that you need to solve. Okay, we need to solve for x. We need to solve for x. Remember the goal. You're trying to find x so that this thing will converge absolutely. To solve for x, you got to get rid of any coefficients around x, okay, which would be this thing right here. Okay, so divide this inequality by n plus 1 limit. We get absolute x plus 5 less than 1 times 1 over n plus 1, right? I need to divide by n plus 1 to solve for x, okay? Absolute value inequalities. And then you can put the limit on the right-hand side. There. All right, take the limit. You get less than 0. So, what does this say? Think about this inequality. What does this tell us? Absolute value of x plus 5 less than 0.
Not going to exist.
Okay, so Alexei, the word undefined is when something does not exist. For example, 1 divided by 0 is undefined. Okay. Or log log of -1 is undefined. It's not real, but if you're talking about real numbers, log of -1 is undefined. Undefined is for something that doesn't exist. We have that versus no solution. No solution is when an inequality or an equation never satisfies, is never satisfied. That's like no solution. Okay, so here we say no solution. All right, because if you think about it, basically anything in absolute value must be non-negative, must be positive or zero. And this is saying that this absolute value, something positive, is less than zero, which makes no sense. Okay, so no x will satisfy this inequality. Therefore, the radius of convergence is zero. The number that you get on the right-hand side, this thing is the radius. That's the radius. This is saying, if you interpret this inequality, interpretation of this inequality is that, guys, make sure you're listening. The distance between absolute value is distance. The distance between x and the center, which is -5. Okay, so if I write that, it's absolute value of x minus -5 less than 0. The distance between, distance is absolute value minus between x and -5 is less than 0. Okay, distance less than 0. So radius, if you think about that 0, it's the radius pretty much, which says that there is no such x. We can't have a distance between x and -5 being less than 0. So no x will satisfy this inequality. So we say there is no interval of convergence. Okay, again, radius is zero, but the series does still converge for what? Only there is only one x value that this thing will converge for. -5. -5 plug in here will zero out every term except for the constant. Okay. The power series converges only when x is equal to -5. Because, yeah, as I said, if you expand the series, so that's n factorial times -5 plus 5 to the power of n, it's gonna give you, so when you plug 0 for n, you get 0 factorial. What do we get? We get 0. Well, I have to expand the series and then I have to plug in. Yeah. So that's x plus 5 to the n. If I expand the series, we have 0 factorial for the first term, plus we have 1 factorial times just 1 times x minus 5 to the power of 1 plus 2 factorial x minus 5 to the power of 2. So if you let x equal to -5, all of these terms go away, all of them, except for that 0 factorial. Okay, so the value of this power series becomes 0 factorial when x is equal to -5. So this is equal to 0 factorial for x equal, sorry, those are plus 5s, for x equal to -5. It converges only when x is the same as the center, and it converges to that constant value. The power series, I don't know what to say. It's singular, degenerate, it has a name. I don't remember what the name is, but it's just degenerate. Yeah, that's it. No interval of convergence, basically. All right. So let's look at a case where we have a power series for when it is convergence for a finite interval, when the radius is finite. Okay, this power series begins at 1. You can, if you want to make it start at 0, you can shift it, shift the index, but who cares? There we go. All right. Yeah, so the nth term of this power series is this. Okay, and again, we want to find the radius and interval of convergence. We want to find x so that it converges. These are the coefficients. This is the this gives you the coefficient, and the center here is 2. Again, you can try and speculate, guys. We can try and predict in advance. You don't have to. You can just go ahead and do the math. But what you want to do is try to find x. Okay. Try to find x so that x minus 2 to the n over 5 to the n will give you a base, right? So these are power n, both of them. Okay, so we want to choose x so that x minus 2 over 5 becomes between -1 and 1, like a geometric series. Okay, we want this to act like a convergent geometric series. So we want to choose, well, I know we have this n over here, so this thing is never going to be geometric. It's never geometric. But this is irrelevant because this is going to be, I guess, the dominating factor. Okay, it's not, n is not irrelevant, but it's irrelevant when we are talking about the long run behavior of this series. We want it to act like a convergent geometric series. So, for example, if I choose 1 for x, we get what? Or 3 for x, we get 1 over 5 to the power of n. That acts like a convergent geometric series. Ratio would be between -1 and 1. Right, so x qualifies to be in the interval of convergence, you know, x of 1, for example, or x of what? X of 3 also qualifies. But we're just gonna do the math, okay? So again, begin by finding the limits of the ratio in absolute value, and then later we're going to make it less than 1 so that it's absolutely convergent. All right, so u sub n plus 1. Okay, so one thing, guys, we have that -1 to the n minus 1. Okay, this is a factor of the nth term. But do I really need to write that factor here when I'm doing? I don't. You could do -1 to the n plus 1 minus 1. You can write it down if you want, but we are checking for absolute convergence. It drops out. After all, we have absolute values. No need to write it down when you're checking for absolute convergence, waste of your time. So drop it. It's not gonna hurt if you write it down, but it's gonna be a complete waste of time. Okay, so we're just gonna drop that factor. We have x minus 2 to the n plus 1 divided by n becomes n plus 1. We have 5 to the n plus 1. That's u sub n plus 1 in absolute value. Multiply that by the reciprocal. The reciprocal will be x minus 2 in the denominator to the power of n. On the top n, 5 to the n. Again, we just drop that -1 to the n minus 1. Okay? Yeah. No need. Okay, so this is equal to the limit of expand u sub n plus 1 or factorize. We have on the top x minus 2 to the n times x minus 2. You can also divide these by subtracting the power. You could do it that way. Bottom, we have n plus 1, can't do anything but that. 5 to the n plus 1 factors to 5 and 5 to the n. We have times, we always leave a sub n or u sub n untouched, the reciprocal of u sub n untouched. Okay, now the feel good part where you cancel x minus 2's, well, no, not that. X minus 2 to the n cancels. 5 to the n cancels out. Nothing else cancels. Do not dare canceling n and this n, okay? I never seen anyone do that, but this is not a factor. This is a term of n plus 1. Can't cancel it. Okay, now if things can get out of absolute value, know what, Ahmed? What are you surprised for?
I was just surprised about how, like you mentioned, to not cancel it. Like, I can't believe like some people would cancel the n and the n plus 1.
It happens.
Yeah.
Not because, oh, you might say, oh, those people are so dumb in math. No, not because of that. It happens because people get nervous.
Yeah, of course.
Okay. I know, like down deep, I know that they know they shouldn't be canceling, but it happens sometimes. People make careless errors. Okay, so again, get things that are positive out of absolute value, and this is a positive factor. N plus 1 is positive. 5 is, it can be taken out of absolute value, so take them all out. We have n 5 times n plus 1. Okay, and absolute x minus 2 must stay in absolute value because we don't know the value of x. That's your unknown. N is always positive. Okay, and again, for the power series to absolutely converge, we want this to be less than 1. Now you have an inequality. Okay, so again, we want to solve for x. All right, you have two options with this limit. You can evaluate the limit at this moment. It'll be 1/5. Or you can get rid of this whole thing, then take the limit. That's what I did previously. As you see, I got rid of that whole thing by dividing, and then I took the limits. I wouldn't want to take the limit here because if I do, I'm gonna get like infinity times absolute x plus 5 less than 1, which kind of would look weird. Okay, so I get rid of the limit and then take the limit. Okay, so this would be absolute x minus 2. So again, to be consistent with what I did previously, this is less than, so you want to get rid of this fraction multiplied by its reciprocal. It'll be 5 m plus 1 over n. And then you could take the limit on the right hand. Okay, it's easier, probably. And that gives us absolute x minus 2 less than 5. That limit, don't think about it too much. Yeah, 5n over n are leading terms, so you get 5. So here we've got ourselves a finite radius of convergence, a non-zero finite radius. It happens to be 5. That radius is 5. Okay. Whenever you have absolute value of x minus c less than r, the number on the right hand is radius. Okay, c is the center. Distance between x and c is less than r. Okay, so here this reads as distance between x and 2 less than 5. Okay, you can either solve this inequality using algebra, or you can solve it using geometry. Okay, draw the number line. Here is 2. Then what you do is go 5 units forward, backwards. That's going to give you the interval. So if I go 5 units forward at 5 to 2, I get 7. If I go backwards, I get -3. Okay, you could do geometry, or you can solve it by breaking it out of the absolute value. This absolute value inequality reads as x minus 2 being between -5 and 5. As we said, from 2, you go 5 units backwards, forward, add 2 to this inequality. That gives you x being between -3 and 7. Okay. So what this says is that this power series is going to converge absolutely when x is between -3 and 7. For all of these x values, if you choose any of these x values and plug them into x, that's going to give you it's going to make this thing r to the n, where r is between -1 and 1. It's going to act like a convergent geometric series. That's what's going to happen. But we know that the series will converge absolutely for x between -3 and 7. Okay, but we are not done yet, because we don't know what is happening at those endpoints. At those endpoints, we know for sure the power series is not converging absolutely, but it can still converge. If you do a ratio test at the endpoints, ratio test is inconclusive. What are endpoints? The endpoints are -3 and 7. Ratio test when x is -3 or 7 turns out to be inconclusive. Okay, so we have to treat the endpoints separately. Okay, a lot of people miss this part on the test. I don't know why, but this is checking endpoints. We're done with 50% of the problem. Okay, so one endpoint is when x is, let's do -3, or we could do 7, who cares? When x is equal to 7, the power series becomes, okay, so take your power series and plug 7 for x. Something interesting will happen. That gives us the sum okay, in the parentheses, we get 7 minus 2, which is 5. 5 to the n. Okay. You no longer are gonna get that geometric behavior, geometric-like behavior. Again, this power series is not a geometric power series, but in the long run, it would be like a geometric, but unless when x is 7. When x is 7, those cancel out and you end up with, guess what we end up with? -1 to the n minus 1. You could write it like this: -1 to the n minus 1 times 1 over n. Or you could just write that over n if you want. But I wrote it this way intentionally because we all know this as, yeah, the alternating harmonic series. Isn't it? Yeah. And we know that this thing does not converge absolutely. Right? We discussed this before in section, whatever, AST section. In absolute value, if you check for absolute convergence, you get the harmonic series, and that is divergent. So this doesn't converge absolutely. We kind of knew that already. But when you run the AST, the alternating series test, this is in fact convergent, which means that this is conditionally convergent. Okay, so at 7, at the right endpoint, this power series is going to converge. If you want to be more specific, you could say it's conditionally convergent. Okay, so what do you do again to check for convergence? You have to run the AST. All right, so here a sub n is 1 over n, and you just have to check the two requirements. Limit as n goes to infinity of 1 over n is equal to 0. That checks out. And then you can check and see if this sequence 1 over n is decreasing. We've already done all of that. But look at that. If I compare a sub n plus 1, a sub n plus 1 is 1 over n plus 1. The relation of that to a sub n is that 1 over n plus 1 is less than 1 over n. A sub n plus 1 is less than a sub n, which tells us that a sub n is decreasing. So that checks out, okay, which says that the power series converges. And again, if you want to say conditionally, be my guess. When x is 7. Okay. So that's when x is 7. We're also going to have to check the other endpoint. The other endpoint is -3 for x. Again, when x is -3, the power series becomes, so what you do is plug -3 into x of your power series. Here is our power series. Replace that x with -3. I'm just going to erase that, put -3 in. Be very, very patient. Oops, sorry. That over n, 5 to the n. -3 minus 2 to the power n is -5 to the n. Okay, so again, we have that base. And it's as if you might say these two cancel out, but be careful because we have the space is a negative. It's a -5. So what you can do is you separate negative and 5 and rewrite that as -1 to the n times 5 to the n. You can distribute that exponent into both of these factors. Okay, properties of exponents, 5 to the n's cancel out. Okay, now you have to combine these factors. Okay, combine them. Right, so if you add the exponents here, I'm just gonna do it on the side. Okay, I don't want to keep rewriting the summation notation, but -1 to the n minus 1 times -1 to the n is the same as -1 to the power of 2n minus 1. Okay, add the exponents. All right, that can be written as -1 to the power of 2n times -1 to the -1 power. First factor, -1 to the 2n, is really a square. You have the square of -1, and that is just a 1. 1 to the n, or just 1. And -1 to the power of -1 is the same as 1 over -1, which is -1. So that gives you -1. Okay, combining these, you get -1. So we have -1 over n. 5 to the n's are gone. What about this series? What do we say? Convergent, divergent? This is what kind of series?
Divergent.
Yeah, it's divergent. This is the harmonic. It's the negative of the harmonic series. Okay, we could factor the negative out of the sum if you wish. You don't have to do that, but we just get the negative of the harmonic series. Okay, so the power series diverges when x is -3. Okay. All right. So we have the interval of convergence. It's from -3 to 7. Exclude -3, include 7. That's it. You don't need to draw. Okay, so where was the center? The center was at center is at 2. Here is 2. That's C. Okay, so go 5 forward, you get 7. Go 5 backwards, you get -3. Okay. Over this interval, it's going to converge, and it's going to converge absolutely. At 7, it will converge. At 3, it will diverge. Okay. Yeah, and it is just divergent everywhere else. Like that. Yeah, I'm just going to write that. Okay. So convergent here, divergent everywhere else.
So Professor,
Yeah.
the reason we didn't do AST here is because -1 to the 2n would always just be positive, correct?
Say what? Sorry. Because
So,
what?
At the end point, right, we got -1 to the 2n when we simplified everything. And that's
Yeah.
why we wouldn't do AST. It's just because it would always be positive now.
Yeah. Yeah. This thing is not alternating. When you simplify that, it doesn't alternate anymore. Simplify. You got to combine. I had to combine these bases. You see that? -1 to the n minus 1.
Yeah.
-1 to the n. When you combine those, you always get -1. Always, regardless of n. This reduces to just -1. Always -1. It's independent of n. So it doesn't alternate. It's just that it turns out the series turns out to be the negative of the harmonic series. This goes to -infinity. It's not alternating. Does that make sense?
Yep.
-1 to the n times -1 to the n. Something times itself is that thing squared, so you get -1 squared, which is +1. -1 to the 2n, -1 squared is just a 1. We don't have an alternating series. Don't forget to check endpoints, guys. Okay? Yeah, and people forget doing that on the test. I don't know why. That's it. So again, what are power series? What are they good for? And I began the section by trying to explain how certain functions can be expressed as a power series. Okay, so what was that example? This example, remember I was showing that little 5-year-old guy. You have this function doing long division. It turns out to be a power series. You can think of that as the sum of a geometric series. This rational function, 1/1 minus x, can be expressed as an infinite sum. This is something we can do with certain functions. Okay, certain functions have a power series representation, like mainly transcendental functions. Transcendental functions that are not algebraic, like ln x, e to the x, sine x, cosine x, they all can be expressed as a power series. Okay, so next section is actually called power series. We're looking at applications of power series representation of functions. So this is where it really gets interesting. And I think this is section 11.9. Yeah. All right, so we actually saw 1 over 1 minus x. I will go back to that later. We could do a lot with that. But I really want to show you guys, and I think I have time, why. So we'll begin with this theorem. Why e to the x? E to the x, finally. Why is this equal to this power series? Right, we actually proved in the last section that this thing is convergent all the time. Radius is infinity. The interval of convergence is all reals, right? Which is in a way consistent with the domain of e to the x. The domain of e to the x is all reals. The interval of convergence is all reals. The domain of that has to do with the interval of convergence. And I did discuss in section for the basic comparison that e to the power of 1, or just e, is the same as the sum of 1 over n factorial. I did mention that. So if you put 1 for x, you get the representation for e. E can be represented as a series. Well, that's proof. And I'm going to write out a few terms. So first term is 1 if you put 0 for n. And then we have x plus x over 2 factorial. That's x squared over 2 factorial plus x cubed over 3 factorial plus, and so on. Okay, so we're gonna prove finally this theorem. Why e to the x can be represented using a power series. Okay, we'll prove why, but in the next section, we're gonna see where they get this thing from. Okay, we're just proving why for now. So here's the proof. I'm going to let y equal to this power series, 1 plus x squared over 2 factorial plus and my goal is to show that y is equal e to the x. Okay. That's what we want to show. Yeah. So I don't know this yet. I'm trying to show this. But I know my y is this because that's what I let y be. I can do whatever I want to y in order to show it's equal to a certain thing. I can integrate it. I can take its derivative. Let's take the derivative of y. So here we're going to find dy dx. Dy dx is the derivative of what I defined y to be. Okay, take the derivative of this infinite sum. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 factorial. Guys, don't think too much about the derivative of these things. I know we have fractions for each of these terms, so you might think quotient rule. No, don't think quotient rule, please, because the denominator is just a constant. Okay, the derivative of f of x over some constant, the derivative of that is equal to f prime of x over the constant. Just take the derivative of the top function, divide that by the constant. You don't need to do quotient rule. For example, the derivative of x cubed over 5 is 3x squared over 5. Okay, do not do quotient rule. The derivative of x squared over 2 factorial is 2x over 2 factorial. Okay, and I'm gonna write 2 factorial as 2 times 1. Why did I do that? Well, the 2's are gonna cancel. The derivative of x cubed is 3x squared. Okay, over 3 factorial. Don't do anything with that constant, but since I have a 3 here, I'm gonna write 3 factorial as 3 times the rest of the factors, 2 factorial. The derivative of x to the 4 is 4x cubed. And then I have a factor of 4, which is common with the factor of 4 of the 4 factorial. So rewrite 4 factorial as 4 times 3 factorial. Okay, so next one will be 5x to the 4 over 5 times 4 factorial and so on. Okay, now cancel. So we got 1 plus or reduce. The 2's cancel, we get x. Plus here 3's cancel, we get x squared over 2 factorial and so on. 4's cancel, x cubed over 3 factorial. So what happened? I took the derivative of this function and the result is the same as the function. Isn't it? So what we just got is the same thing as y. That is what y originally was. Okay, what we got here is dy dx equal to y. That's what we have. This is a differential equation. Dy dx equal to y is a differential equation. Remember differential equations, section 7.5. We can solve this differential equation by separating variable. You can multiply by dx, you can divide by y, write it as dy over y equal to dx. And then we can integrate. The antiderivative of dy over y is ln of absolute value of y. Antiderivative of dx is just, what is it, x, and then we get some constant of integration. Okay, we want to solve this equation for y. All right, and I also need an initial condition, right, so that I can find the c. We'll discuss that in a second, but to solve for y, just exponentiate. So you get e to the x plus c. Now we see that e to the x. Okay, I can separate that e to the x plus c as e to the x times e to the c, call this c1. E to the c1 is a constant. E to a constant is another constant. So here we get absolute value of y equal to c times e to the x. Okay, just call e to the c1 to be c. Now I need to find c. I'm almost done. We're proving that this thing is e to the x. For us to find c, I have 1 more minute. I need a point on the function. Okay, any point. I need a point on the function y. Here is your function. Just choose a point on it. Any point that satisfies this function. Let's choose 0 for x. So again, note that y is equal to 1 plus x squared, and so on. Okay, here let x be 0, then y is equal to 1. So 1 plus 0 it's just 1. When x is 0, y is equal to 1, notice that 1 is a positive here, so I can drop the absolute value. Okay. Now plug it in. We get 1 equal to so I'll plug into absolute value of y equal to c e to the x. We get 1 equal to c e to the 0. That gives us c equal to 1. Okay, therefore, y is equal e to the x. Okay. Yeah, absolute value drops out. C is 1, e to the x, and that is the proof. Y is e to the x. All right, but again, absolute value drops out because we got a positive here. That does the proof. And I'll see you tomorrow.
Thanks, Professor.
Thank you, Professor.
Thank you.
Thank you.
Welcome.
Professor, do you